Let P be a point of a surface S such that P is not an umbilic point. Then there is a surface patch sigma of S containing P whose first and second fundamental forms are E du square plus G dv square and L du square plus N dv square respectively for some smooth functions E, G, L and N. The proof. Now we have the point P on a surface S and it is not an umbilic point. So the principal curvatures at this point for a surface patch are distinct because it is not an umbilic point here. Okay, so we have to find out we need to search for a surface patch of this surface S containing this point P whose first fundamental form and second fundamental forms are given by this. So first let us start with the surface patch sigma tilde. Okay, so for the surface S, okay, let us consider the surface patch sigma tilde of S, and it contains, let us say that it contains the point P here. Okay, so if this point U is U naught tilde V naught tilde in U, then the corresponding image is P, so I can call this P as sigma tilde of U naught tilde V naught tilde here. Okay, so hypothesis is that the principal curvatures are distinct. If K1 and K2 are principal curvatures of sigma tilde at the point P, then K1 is not equal to K2 because P is not an umbilic point. And we also know that these two are continuous. Okay, principal curvatures are continuous functions, so they remain distinct in some open set, okay, containing the point U naught tilde V naught tilde on which this sigma tilde is defined. Okay, so both are continuous, so they remain distinct in some open neighborhood of this point of the set U tilde here. Okay, let me consider this as U tilde here. Fine. Now let us consider the eigenvectors for these. So if I consider xi I eta I, okay, the non-zero eigenvectors of f2 tilde minus ki f1 tilde, okay, for I is equal to 1, 2. So consider the non-zero eigenvectors of this. So what is f1? f1 tilde, it is the matrix associated with the first fundamental form of sigma tilde, and f2 tilde is the matrix associated with the second fundamental form of sigma tilde. Okay, then what are the principal vectors corresponding to these principal curvatures? They are expressed in terms of these. So the principal vectors corresponding to K1 and K2, they are given by, say, E1, that is xi1 sigma U tilde tilde plus eta 1 sigma V tilde tilde, and E2 xi2 sigma tilde U tilde plus eta 2 sigma tilde V tilde. Okay, these are the principal vectors corresponding to K1 and K2. Okay, and we have proved in the earlier result that if K1 and K2 are distinct principal curvatures, then any two principal vectors corresponding to these will be perpendicular to each other. So E1 will be perpendicular to E2. So E1 is perpendicular to E2 because K1 is not equal to K2. Okay, so if necessary, I will divide this E1 by its norm and E2 by its norm, and I can assume that both E1 and E2 are unit vectors. Okay, let us assume that they are unit vectors. Otherwise, we can divide them by their norms to get them as unit vectors. Now, let us consider the reparametrization of sigma tilde. Let me take it as sigma. So, let sigma be a reparametrization of sigma tilde. Okay. Now E1 and E2, how are they? They are perpendicular to each other. So if you consider sigma U dot sigma V, that is equal to 0 because E1 is perpendicular to E2. Okay. So once sigma U dot sigma V is equal to 0, the second coefficient in the first fundamental form of this will be equal to 0. So F will be equal to 0. So what is the first fundamental form of sigma in this case? It will be E du square plus G dV square. There is no F term here because F is equal to 0, because sigma u dot sigma v is equal to 0. Okay. Now also, what are these sigma u and sigma v? They are principal vectors corresponding to k1 and k2. Okay. So what we have that by the definition of the principal vector, we have f2 minus k1 f1 into 1 0, that is equal to 0, and f2 minus k2 f1 into the other vector 0 1, that is equal to 0. I should write that in the matrix form. Okay, 0 0. So again, what are these f1 and f2? They are the matrices associated with the first fundamental form of sigma and second fundamental form of sigma respectively. Okay, now according to this statement, the fundamental form of first fundamental form of sigma is E du square plus G dV square, and we have f is equal to 0 here. So what is this matrix f here? It is E 0 0 G, because f is 0. Okay, so what will be f2? F2 will be K1E 0 0 K2 G. Okay, so with the help of this matrix, I can write for the second fundamental form of sigma. So what is the second fundamental form of sigma? It will be equal to L du square plus N dV square. What are these L and N in this case? L is equal to K1E and N is equal to K2G. Okay, so these are the first fundamental form and second fundamental forms of the surface patch sigma. So there is a surface patch sigma of S containing P such that its first and second fundamental forms are given by these expressions.